Okay, so we'll continue from last lecture, which we discussed the discrete and the continuous dynamical systems. And we started to analyze just in a two-dimensional continuous dynamical system, what are the possible modes of stability and instability. Right, so coming back to our lecture last week, we randomized a bunch of 2x2 matrices and computed how the trajectories around a fixed point of the simple dynamical system du dt equal to a times u, right, where a is the randomized matrix, would behave. So essentially, we initialized 1,000 random starting points around the origin and see how these trajectories would evolve. So we have seen that we can have an in spiral like this, right? Another in spiral like this, and I think this is unstable spiral, so out spiral, and we can also have cases like this is a saddle point and another bunch of out spirals. So we have all kinds of different ways the trajectories can behave around the fixed point. So today we are starting to associate these different behaviors with eigenvalues. And now we are going to be generalizing the concept of eigenvalues and stability around the fixed point, not just for linear systems, but for nonlinear systems. And then we are going to extend our algorithms for analyzing the behavior around the fixed point from a small linear system to a small nonlinear system to large nonlinear systems, where it might be impossible to obtain a full matrix, right, that describes the behavior around the fixed point. So we'll see that the algorithms will actually derive and demonstrate this week. Some of them actually almost trivially generalize to nonlinear dynamical systems that are not just around the fixed point, but with periodic cycles and even with chaotic trajectories. So this is why we start with simple systems that are fixed points, and the algorithms are a lot more intuitive around the fixed point, but then it'll be naturally extensible to chaotic systems. Okay, so let's look at this equation du dt equal to au first, right? And when we have a linear system du dt equal to au, we can always decompose the matrix into a simple canonical form. So A would be equal to V times gamma times V inverse, where for a 2x2 matrix, the gamma can take a form of either two eigenvalues, lambda 1, lambda 2, or if the eigenvalues are identical, take the form of lambda 1 and lambda 1 and 1. All right, these are the only two possibilities. And in case of the eigenvalues being different, right, because A is a real matrix, when the eigenvalues are the same, they can only be real numbers. But if the eigenvalues are different, they can either be both real numbers or a complex pair of conjugate values. So when we're able to decompose the matrix like that, we can write our dynamical system du dt in a similar form. That would be equal to V times this lambda times V inverse times U. All right, now if you look at the matrix that way, we can always decompose not just the matrix, but also the initial condition U at time 0 as the linear combination of the two of the eigenvectors. Okay, so that is assuming that basically V, again, is a matrix. And we can write V as, let's see, two components, so V1 and V2. So each of these V is a vertical, it's a column vector. Okay, so then you can represent the initial condition U0 with the U1 times V1. So U1 is a scalar, and V1 is this column vector, plus U2 times V2, right? Okay, so then we can always represent the U also as a function of time, always using U1. Now this is at time 0, this is also at time 0, as a function of t times V1 plus U2 as a function of t times V2. And then once you plug this into the differential equation, what you get is these two modes, U1 and the U2, are going to be two separate differential equations, right? I mean, we are essentially removing the coupling, the two-way coupling between these two differential equations. So let's look at this decoupling in two different scenarios. First of all, when the A has two distinct eigenvalues, right? What happens is when you plug this into the equation, into this equation, we have the du1 dt times v1 plus du2 dt times v2, so that's the left-hand side, would be equal to v, which is the composition of v1 and v2, times the diagonal matrix lambda 1, lambda 2, right? Then times v inverse times this. So what is v inverse times this? V inverse times this can be written as v inverse. Actually, you can represent this actually into a matrix form, right? If you represent this into a matrix form, you get v1, v2, which is v times u1 as a function of t, u2 as a function of t. So, right, so this is familiar with the matrix vector multiplication, right? So this matrix times this vector is simply v1 times u1 plus v2 times u2. Okay? And because this is just the matrix V, it cancels with the V inverse. So this whole thing goes away, and you're essentially having lambda 1 times U1 and lambda 2 times U2, right? The whole right-hand side then becomes so the whole right-hand side, if you just do all the matrix vector multiplication, so lambda 1, the diagonal matrix times the vector is just another vector, right? They just multiply each entry on the diagonal matrix with the corresponding entry, right? Then we have another matrix vector multiplication, so the end result is going to be lambda 1 u1 times v1 plus lambda 2 u2 times v2. Okay, so now here you can clearly see that this equation can be really decomposed into two independent equations. So basically du dt, which is aligned with the v1 direction, that's a different direction from the v2 direction, right? So this term by itself has to evolve on the independent trajectory. du1 dt equal to lambda 1 times u1, and the du2 dt aligned in the v2 direction is going to be equal to lambda 2 times u2. Right, these are the two separate equations. Now, in the case when the two eigenvalues are the same, okay, then basically the lambda, instead of being a diagonal matrix, you have an upper triangular matrix. In that case, the two equations would be coupled, but the coupling would be a one-way coupling. Okay, so instead of, if you look at the original equation, the two different components of u are interdependent. And in this equation, the two components of u, after you look at, instead of looking at just the two components, you look at the two eigencomponents, they are independent. While in this case, there is a one-way dependency. So the first direction would not depend on the second direction, but the second direction would, I think I said it the other way. So the second direction corresponding to the second V, right? If you look at the V's again in the two columns, would not dependent on the first direction, but the first direction would depend on the second direction. Okay, any questions? Yeah.
So when you write the combination of two linear components, it's like approximation, or is it exact value?
It is exact, right? So in this case, in this case, when you write A into this form, you know V is invertible matrix, right? So you can actually exactly calculate what U1 and U2 is by multiplying the inverse of V with U0.
Because the system of equation is linear, it becomes the exact one, right? It's like the exact.
So it should be linear. This set of equations all is strictly linear, right?
Yes.
Right now. Yeah.
Yes.
Okay.
So if our equation is dynamical system is nonlinear, is it also the exact decomposition, or it's gonna be approximation?
Yeah, if the system is nonlinear, that's a good question. Then what we are really would be doing is looking at an infinitesimal perturbation around the fixed point. And it is an approximation if you think about the dynamics near the fixed point. But if you think about the infinitesimal small neighborhood around the fixed point, then again, this is going to be exact. Right? The approximation is really an approximation of a limit of tiny perturbations. Okay, so now what this means is that once you're able to rotate, once you're able to look at the dynamics not in the raw coordinates, but in the coordinates of the eigenvectors, the V's, then it doesn't matter what the V's are. The only thing that matters are the lambdas, right? The only thing that matters is the matrix in the middle, right? Because if you just define your U in a different way, right? No matter what V is, the dynamics would be actually identical. It'll always be. So if you treat the V inverse U as my new vector, right, and move this V to the left-hand side, basically the equations would only depend on lambda. So that is why we can really categorize the stability properties of this 2x2 system in terms of just two numbers, the lambda 1 and lambda 2. And in particular, we can categorize the stability properties of all the graphs we have seen, right? All the behaviors we have seen by using two numbers. One is the trace of the system, which is lambda 1 plus lambda 2. So this is lambda 1 plus lambda 2. And the other is the determinant of the system. So that is going to be equal to lambda 1 times lambda 2. Okay, so conveniently, the trace and the determinant is actually both invariant to a transformation like this. So the trace of A is going to be equal to the trace of lambda, which of course is lambda 1 times lambda 1 plus lambda 2, right? The trace of A is just the sum of the two diagonal numbers in the matrix A. And if you're familiar with linear algebra, there is a pretty simple proof that if you perform a similarity transformation to a matrix, the trace would be preserved. Another thing is that the determinant, again, is also independent of a similarity transformation. So the determinant of a matrix is always equal to the product of the eigenvalues. So when the product with eigenvalues are negative, that means two things. One is the eigenvalues are distinct, right? It's not possible to have a the same eigenvalue like squared to be negative, right? No matter if the same eigenvalues are real or a conjugate pair of complex numbers. If you multiply them, they are always going to be positive. So when they are negative, you are going to know that you have two real different eigenvalues, and one is positive, one is negative. That's why it's always a saddle point, right? So going back to our graph, dynamics like this would mean an eigenvalue positive and eigenvalue negative. So here, for example, we can always so every time we make a figure, right, we can make a title of the trace. The trace would be equal to the diagonal of A summed up, right? So maybe this is font is too small. It's good enough, I think. Okay, and determinant would be equal to I think linear algebra dot determinant. Do I need linear algebra? Yeah. Okay. A. All right. So let me rerun this, and every time I have a system, it'll actually put on the title what are the two numbers, and we'll see how different they are. So on the other hand, when the delta is positive, there are many different scenarios. Okay, so what's interesting is there is a parabola over here that determines if that basically has to do with the sum and the product. That has to do with if the solution to the quadratic equation gives you a set of real numbers or gives you a pair of complex conjugates, right? So basically, if you set up these two equations, both the product and the sum, you get a quadratic equation, right? You solve them, you get the pair of real or conjugate complex numbers. So when this thing is less than 0, you get a complex conjugate, and then it'll also depend on if the real part of this complex conjugate is positive or negative. If they are positive, you get an unstable spiral. If they are negative, you get a stable spiral, right? And on the other case, when you have a pair of real solutions, it again depends on if the pair of real solutions are both positive or both negative. If both positive, they are the unstable nodes, and if both are negative, they are stable nodes. So let's go back to our plot. Okay. And look at the new titles of our so here you see the determinant being negative, right? So we get a what? Get a saddle point, right? So that's pretty obvious from here. And again, another negative determinant, a saddle point. Now here we get a positive determinant, right? And the trace is negative. That means it's a stable spiral, right? We didn't compute this number, so the square of the trace minus 4 times the determinant. But like if you do the calculation, you're gonna see it's gonna be negative, right? So 4 times determinant, if you square it, is about 0.1, right? And yeah, that's clearly less than the 4 times determinant. So here, what we get is it's a stable center, right? So a positive determinant, and the trace is large enough compared to the determinant. I mean, the square of the trace is large enough that we get real eigenvalues. So again, positive determinant and a small trace, which means spiral, and this is going to be an unstable one because the trace is positive, right? So you can go through all of these and and see the eigenvalues really explains the dynamics around this fixed point. Okay, any questions before we go to actually how do we compute these eigenvalues? Okay, so this is, as we can see in the 2x2 case, it's pretty simple, right? The eigenvalues can be computed by really just computing the determinant, computing the trace, and solving a quadratic equation, right, for the two solutions. But as we go to higher dimensions, it is no longer as simple. So this lecture will spend some time in figuring out how do we actually compute eigenvalues, and especially for larger and larger systems. All right. Okay, so how do we computationally assess the stability of a nonlinear system? So the first method is to actually derive the so-called tangent equation. So the tangent equation is something we'll study a lot, not just for stable near fixed points, but also for periodic cycles and chaotic systems. All of them has the so-called tangent equations. So the tangent equations is the equation that governs an infinitesimal perturbation to a nonlinear system. Okay, so if you have a system, let's say again we'll just look at the both maps and differential equations.
Tangent of A, basically, the matrix A becomes a tangent at a certain time. That's what.
Yeah, so basically it gets you a linear equation from a nonlinear equation, right? So for example, like if you have if I have a map uk plus 1 equal to f of uk, the tangent equation governs the dynamics of a tiny perturbation. So that means if my uk is perturbed, right, into uk plus an infinitesimal epsilon times vk. So v is the direction of the perturbation, and the magnitude of the perturbation is always infinitesimal. Okay, then my uk plus 1, then I mean if you apply this map to the perturbed state, then the mapped state is no longer going to be exactly equal to uk plus 1, right? It's going to be uk plus 1 plus an epsilon times the same epsilon times some perturbed direction we call v of k plus 1. So the tangent equation is the equation that governs the evolution from vk to vk plus 1, right? So what is the dynamics that governs the transformation from vk to vk plus 1? Well, that can be derived by linearizing this nonlinear map, right, using the first order Taylor series expansion. So using Taylor series expansion, what we get is the first term is f of uk. And what's the second term? The second term is something proportional to epsilon, right? Yeah, it's the Jacobian partial f partial u at the location of uk times vk, right? And our Taylor series contains other terms, but these are going to be proportional at least to epsilon squared, right? So if epsilon is infinitesimal and if the Jacobian is not singular, right, then all of these would be negligible compared to the first two terms. So by epsilon being infinitesimal, that's the approximation I think you are concerned about, right? We can rightfully ignore the high order terms. And as a result of that, because uk plus 1 is equal to f of uk, right? So the largest term actually cancel out, and this term the second most important term that's proportional to epsilon but not proportional to epsilon square would have to be equal to each other. So these and these actually cancel out. So what we get is the tangent equation. Vk plus 1, of course, divide both sides by epsilon, would be equal to partial f partial u at uk times vk. All right. So this is for maps, and for differential equations, it's almost exactly the same. So if you have a differential equation du dt equal to f of u, right? And of course, u is a trajectory, a function of time. But if you consider an initial condition, if you perturb the initial condition from u0 to u0 plus epsilon times v0, and v0 is the direction of the initial perturbation, then the trajectory is no longer going to be u as a function of t. It's going to be u as a function of t plus an epsilon times v, which also would evolve as a function of time, right? So now if you plug this into this equation, what you get is du dt, that's this original u, plus epsilon times dv dt would be equal to f of u plus epsilon v. And again, by the Taylor series expansion, what you get is f of u plus epsilon times the same df du at the u location times a v. And again, because the du dt terms cancels with the fu term by the original equation, right? What you get is again the tangent equation. The tangent equation is going to be dv dt equal to df du at the u location times v. So that's my tangent equation. Yeah. So these tangent equations, in the future, we may call them a homogeneous tangent equation, because these are the equations. It's a homogeneous linear equations, right? They correspond to the case where the initial condition is perturbed, but the map or the differential equation itself is not perturbed. You can also derive a slightly different set of linearized equations or tangent equations that corresponds not to an initial condition perturbation, but to a slightly perturbation to the map or the equation itself. Yeah?
So homogeneous means that we have perturbation at the start, initial condition, right?
Yes, homogeneous means the right-hand side of the equation is totally proportional to the solution.
But if we perturb some extra parameters like the angle of attack or mesh,
Yeah, it's not going to be the case. So if you perturb the angle of attack, you're modifying the equation, right? And then the right-hand side of the equation would contain two terms. One term is proportional to the solution. The other term is a constant. All right. So that'll be like the right-hand side is ax if you have a homogeneous equation. The right-hand side would be ax plus b if you have an inhomogeneous equation. All right, that would the b would actually contain information of how the equation would be perturbed. We'll look at that later. All right. Any more questions? Okay, so now let's actually get into the algorithm for actually figure out what the linearized equation would be, right? Because the linearized equation would actually contain all the information of how the dynamics would evolve around the fixed point. By around, I mean like infinitesimal neighborhood, right, around the fixed point. Okay, and we are going to see that whatever we derive actually, in a lot of cases, governs a noticeably larger neighborhood around the fixed point rather than just the infinitesimal. So here, let's just start to look at one of the equations we'll use a lot to first demonstrate any algorithms. This is the Lorentz equation, right? The Lorentz equation is kind of a famous example in dynamical system study, just because it's so simple and it can illustrate the dynamics of a large range of different different dynamics. So let's actually continue on our notebook, and just after that we'll make another new section, and we'll define the Lorentz system, U and T. So in order to make our integration a little bit more efficient, let's actually assume that U, instead of being a single solution, U actually contains a collection of solutions, an ensemble of solutions. Okay, so let's say X, Y, Z, which is equal to the 3 states of the equation. Let's assume instead of U being a vector of 3, let's assume vector being a vector of 3 times n, where n is the number of solutions in the ensemble. So we are going to reshape U into 3 and would have a dimension that multiplies with 3 to form as the the size of U. Right? Are you familiar with the reshape operator in Python? Okay, NumPy. So basically, -1 means whatever dimension that is, whatever size that's required to multiply to the original size. Okay, then there are 3 parameters, sigma, rho, and beta, that that changes the dynamics of the Lorentz equation. And today, let's just start with a very canonical set of parameters. Sigma is equal to 10, and the rho. So let's set rho to 0.5 for now, because as we are going to go more and more into the lecture, we are going to actually ramp up rho into higher and higher values. And when rho is high enough, you are actually going to see chaotic dynamics. Actually, let's first demonstrate the chaotic dynamics of the Lorentz equation before we ramp it down to study the fixed point behavior. And the beta is usually set to 8/3. So these parameters are what Edward Lorenz, a professor at MIT back in the 1960s, used to model the convection in the atmosphere. And the beta is so the beta is a parameter that describes the shape of the convection cell, and the rho is a parameter that defines how big the temperature difference is between high in the atmosphere and low in the atmosphere.
For like this model, can you? I mean, you went through it a little bit, but are you able to, like, for each term, say a physical meaning of what each term means in the Lorentz system? Like,
Yeah. So
when I look at it, it just kind of looks a little random, you know?
okay, yeah, sure. So let me see. So X and Y and Z are basically truncations of the temperature and the velocity distributions, right? So in the Fourier series.
Okay.
So essentially, what you can do is you can describe. So first of all, it's a 2-dimensional model. So you are assuming the velocity and temperature are all just functions of 2 dimensions, while the 3rd dimension is homogeneous. And to derive this model, it is also assumed that how the temperature and velocity varies follows only the first sinusoidal component, right? So basically, you are truncating the Fourier series. All the high frequency components get removed. Okay, and I don't remember exactly the variables, but one of them. So I think 2 of them are related to the temperature distribution, right? So if you look at the temperature distribution, and there is going to be inequilibrium both in the x direction and in the z direction, where varies with height. And the 3rd variable relates to the speed of rotation of the convection cell. So maybe I can look at it a little bit later and tell you in the next lecture what exactly how the equations are derived. But from a very intuitive point of view, so one of these are really just a linear advection of how the so this is just a linear, right? So the linear advection is really how the x and the y direction of the temperature distribution just rotates into each other, right? So that's mostly the dynamics of x and y. And there is another component, dy dt, probably corresponds to the vertical temperature in equilibrium, right? So that is not only a rotation that relates to x times y, but also has to do with the rho, which is how much the temperature got heated up at the bottom. So that will also change the vertical temperature distribution. And another thing is so z, I think, is the velocity of the rotation. It's basically derived as there is a minus beta. That's kind of the that's like how the velocity gets. There is a friction term, right, in how the velocity is slowed down, and it's also a function of both the horizontal and vertical in equilibrium. Right, so I'm not sure what I said is exactly correct all the way, but like this is what I remember from the derivation I read about some time ago.
It's like a Rayleigh-Bernard.
Yeah, it's Rayleigh-Bernard. Yes, right. It's a extremely simplified Rayleigh-Bernard convection. Okay, now we implement this into Python. So dx dt would be equal to sigma times y minus x, and dy dt would be equal to x times rho minus z, and that minus y, and dz dt would be equal to x times y minus beta times z, right? Okay, and when I return the time derivative of u, I need to put these three vectors together, right? So I would squeeze means just remove the multidimensionality. Just to put, I think ravel would be the right thing to use. Ravel would be, but yeah, return a contiguous flattened one-dimensional array. So dx dt, dy dt, and dz dt. All right. So that basically is encodes the dynamics of the Lorentz equation. All right. Okay. So let's actually initialize a bunch of u0s and make it just again random.rand, make 1,000 trajectories. Actually 3 and 1,000. So 3 would be xyz, like the three components. 1,000 is 1,000 ensemble of 1,000 trajectories. Okay, and I would say u would be equal to od int and Lorentz u0 and space. Let's make it 0, actually 0, 100, and 101. So let's actually try to visualize the chaotic dynamics of the trajectory first. So, sorry? Oh, yes. Yeah. Thank you. So that'll make it indentation does not match. Okay. Okay, so it expects 2 numbers instead of a list. Okay, so now the integration is done. So you should have a shape of the number of time snapshots and the dimension, right? So let's actually visualize that. So let's reshape it. into the shape we expect. So that'll be u dot shape 0, so the number of time instances, and 3 and the -1, right? And let's actually plot u as a function of time, and the first dimension against the u. Let's plot the third dimension. Okay. I think I might have done it. Yeah, I think I might have done it with a 2 cos of a time step size. So let's actually make the time step size 0.01 instead of 1, right? And that'll make I think the visualization a little bit better. It's plotting 1,000 lines, so it'll take some time. Maybe I should stop it and just plot. Oh, okay. So that works. Yeah, so that's the fully fledged Lorentz attractor you've probably seen elsewhere, right? So basically the solution would start around this point, and depending on where the initial condition is, although the 0, 0, 0, if you look at the equations, is a fixed point. So if x, y, z are all equal to 0, dx, dt, dy, dt, dz, dt are all should be equal to 0. But in this case, the fixed point is unstable, and the solution either comes to the left or goes towards the right, right? And eventually they fill the strange attractor like this. But today, let's actually don't look at this case yet, and let's look at a case with a much smaller rho. So let's make rho equal to 0.5 and integrate the equation for much shorter time, only 1 time unit, and look at the dynamics around that fixed point. Now, if you plot them, let me actually use something to capture that, so that we don't display too many stuff. What you see is something that looks a lot more garbled, right, around the fixed point. But because we have 3 dimensions, let's actually plot all of them to take a look. So let's actually make okay, so let's actually make several subplots and plot this in one of the subplots, and plot x versus y in another one, and y, actually z versus y at a third one. All right, so if we do that, we get something like this. So actually, let's make it a little bit bigger, so that it's easier to see. Okay. Doesn't respond anymore. Yeah, maybe I should launch another tab. Refresh it. Okay, let me just use something to capture that. Might be a bit better. Okay, so let me make it a little bit bigger, 16 and 9. So so that it's easier to see. And let's actually label them. Doesn't work. So that's X and Y, and that's Z and Y. Okay. Okay. To do set X label. Right. Okay. So this is what you see. Actually, we see that only when, oh, this should be Y label, sorry. So only the X versus Z plot looks messy, right? The other two plots, especially the X versus Y plot, looks very clean. And it also looks like what we have seen, right, in the two-dimensional dynamics. So if you examine the X versus Y plot, what kind of a fixed point does that look like? Yeah, so it is like the nodes. There are two directions, right, where the flow goes straight into the origin. So you can see that there is a diagonal direction that goes into the origin that's stable, right? There is another direction that's almost horizontal, right? So if you come here, you're seeing the trajectories curve like this way, but if you are underneath, you see the trajectory curves up. So in the middle, there is a bunch of trajectories that goes right in to the origin. So there are two stable modes, right? And we can see that the one stable mode, by the way, which stable mode do you think is much stronger, that converges much faster? Yes, the almost the horizontal ones, right? Because we can see if you start from a corner, it goes horizontally first, and when it goes almost along this diagonal line, then it starts to slowly converge to the center. So let's try to figure out, can we use the concept of a tangent equation, the dynamics around the fixed point, to explain this phenomenon, right? And another thing is, can we also explain the phenomena that when you look at XZ plot, it looks completely random, right? There doesn't seem to be any correlation, any dependence, right, between how the dynamics works in the X direction versus how the dynamics works in the Z direction, right? Why is that the case? Okay. So first of all, let's actually derive the tangent equation. What is the tangent equation of this Lorentz equation? To do that, we're going to study multiple ways of looking at the tangent equations, but the simplest way, the most also non-intrusive way to look at the tangent dynamics is to actually just perturb the input a little bit and look at how the output, what F would produce. So this is exactly following the definition of the tangent equation, right? So essentially, we are going to be making infinitesimal perturbations on the input to the F and look at how the output would be perturbed. And in this particular case, we know that if U is equal to 0, okay, F of U would be equal to 0, right? So that means if we can perturb U a little bit from 0, we would be able to examine how df du works. Okay, so here what I'm going to be doing is V is going to be equal to I of 3. So why I of 3? Why identity matrix? Because we are choosing 3 directions of V that's orthogonal to each other, right? And essentially, if we choose 3 directions of V, that's 1, 0, 0, 0, 1, 0, and 0, 0, 1. We are going to be computing, each time we are going to be computing one column of the matrix DFDU, right? If you multiply the vector 1, 0, 0 onto this, we should get the first column of DFDU. If we are multiplying 0, 1, 0 with this matrix, we are getting the second column. All right. So basically, and what we are going to be doing is epsilon. Let's make it something very small, 10 to the minus 8, for example. Okay. And then we're just going to be calling the Lorentz. So DFDU, and we usually just call it, let's say, the Jacobian. Right, that's the matrix form of the derivative of a nonlinear operator. So this is going to be Lorentz of V divided by epsilon. So let's actually look at what J is like. It needs me a T. Okay, so let's print J. Okay, so we also want to reshape it. So basically, yeah, how do we reshape it? So we know that the first dimension has to be 3, right? So that's always how we reshape it. And the first dimension corresponds to X or Y or Z. And the second dimension corresponds which solution it corresponds to, right? The first, so the second dimension is the columns of the array, right? The first dimension is the row of the array, and the row of the array denotes which variable it is in the V, right? The first row corresponds to X or a small perturbation X. The second row corresponds to a small perturbation in Y, etc. Now the second dimension corresponds to which column the array is, and that corresponds to which initial condition it corresponds to. The first column corresponds to the initial condition, that is epsilon times 1, 0, 0. The second column corresponds to the second initial condition, etc. So this is exactly the matrix we want. Oh, sorry, not V0, but V times epsilon, right? 0. Okay, so then this is going to be the matrix. Well, of course, this matrix can be analytically derived, right? As you can see, these numbers, minus 10 is exactly minus sigma, right? And the 0.5 is exactly rho, and minus 2.666 is exactly minus beta. So you can analytically derive this, but as we can see later, doing things numerically actually generalizes a lot better when you are encountering systems where deriving things analytically is either involves just too much human work, or it may not even be feasible. Okay, so right, so this is really the DFDU matrix we've been looking for. Okay, if you multiply the matrix with 1, 0, 0, it gets you exactly the first column, right? So that's how that mode is going to evolve. And what's particularly interesting is that let's actually not just print J, but also print the eigenvalues of the matrix J. So linear algebra.eig of J, and it returns both the eigenvalues and eigenvectors. So let's look at the eigenvalues first. So these are the eigenvalues of the matrix. Okay, the eigenvalues has a minus 10 component, has a minus 0.4 component, and has a minus 2.66 component. And what's a little bit more interesting is how does the eigenvectors of the matrix look like, right? So these eigenvalues essentially tells you that all of these modes have negative eigenvalues. What that means is that the system is stable, right? So no matter how you perturb it, no matter which eigenvector direction you are perturbing the system, you have the magnitude of that perturbation follows a ordinary differential equation that is du dt equal to something negative times u. So things converge exponentially to the origin. But let's also print the eigenvectors, and we'll see how that illustrates the graph we see above. So the columns of these are the eigenvectors. Note that the sign of the eigenvectors doesn't matter, right? The first column can easily be positive 0.99 and then negative 0.05. And this column corresponds to the most negative eigenvector. Most negative eigenvalue, right? That means if you perturb the initial condition in this direction, that perturbation would converge to the origin at the fastest rate. And if you think about what this direction is, right? -1, almost -1, and 0.5. That's this direction, right? This is exactly the direction which the perturbation goes to the origin at the fastest rate. Another thing is the second row. The second row is -0.72 and -0.69. So these would be almost diagonal, right? And the rate of convergence -0.47 is much slower. So that is this. That is exactly this one coming in. The third observation is that when you look at both the first two eigenvectors, they are strictly in x and y. There is no z component. While the third eigenvector is just the z direction. So this is basically saying that the perturbations in the xy directions are decoupled from the perturbation in the z direction. And that is why when you look at the xz plane, it looks just completely random, right? And when you look at the yz plane, you do see something, but what you actually see is that just the convergence in the z direction is faster than the convergence in the y direction, and that's it, right? There is not much else you can say from this. But like if you look at these things, the trajectories do cross each other. They don't align very well. Okay, and the reason this plot looks particularly messy, right, is really the fact that if you just look at x, so if you slice, if you forget about y, just look at the particular x, the direction of convergence is not. I mean, you can, if you start from here, x can go negative. If you start from here, x can go positive, right? So at one particular x, there is no clear direction where x is going to go, right? That's it. Okay, any questions regarding to how the dynamics of the Lorentz equation works near the origin?
To get the point for the messy plot, why it became messy?
Yeah, it's messy because there is no dependence of how the dynamics work in x and y versus how the dynamics works in z.
But in the eigenvectors, is there any sign that we can?
Yes, the eigenvectors are they are separate, right? So the x and y forms a block that's separate from this block. So when you see something like this, what it means is that you can really decompose the tangent equation into two components. One tangent equation only works in the x and y direction, okay, and the other just works in this direction. it can be seen from the matrix from the Jacobi, right? So you get 2 zeros over here and 2 zeros over here. What that means is that if you know just the perturbation in x and y direction, you can compute exactly what the dynamics in the x and y direction is without knowing the z component at all. And if you know the z component perturbation, you can derive the dynamics in the z component without knowing what x and y is at all. This is the physical meaning of these 2 zeros and these 2 zeros, right? So that just means if you look at the plots, right? If you know, yeah, that basically means that you have two dynamics that goes independently. So that's why it looks like that. This is in contrast to this plot, and the dynamics in x and y are completely dependent, right? So that's why you have a neat plot like this. If you basically, this is saying if you know what is x and y location, you know exactly which direction it is going. And this is saying that if you only know x and z without knowing y at all, you have no idea where the solution is going. Okay. All right. Okay. So this is basically what you can do to the dynamics if you are able to perturb in every single direction possible, right? So it works completely fine for a small dynamical system like Lorentz, and I mean, this is actually one of the reasons we love using Lorentz as a case study, just because it is so small. But for systems that we are usually interested for physical reasons, like turbulent flows, it is simply impossible to construct an identity matrix, right, that is of the same dimension as the system itself. Just to give some simple examples, for most computational fluid dynamics simulations of turbulence, the dimension of the system is at least several million and can easily go to several billion or tens of billions. If you make an identity matrix and computing the Jacobian by applying the nonlinear physical law to the identity matrix, simply means that performing the same simulation, which is already expensive, for millions or even billions of times, right? So that is simply not a feasible thing to do. So that is why when we are looking at ways to study the dynamics around no matter fixed points or chaotic trajectories, we are usually thinking about not actually analytically computing the Jacobian matrix, but be able to compute the properties of the Jacobian matrix without having the matrix at all. So what can you do to figure out things about the Jacobian matrix without having the matrix at all? Okay, so that's a question that we want to answer next, right? How do you assess the stability of large systems? Now imagine you have a function f of u. Okay, imagine you are able to compute f of u plus an epsilon v, right, minus f of u divided by epsilon. That, you know, when epsilon is very small, it's approximate to df du at this u location times v, right? So again, that's our first order Taylor series expansion. So what you are doing here is you are approximating the multiplication of the matrix with a vector. So anytime you perturb a simulation, perturb the state, and evaluate it, you are essentially performing a matrix vector multiplication if the perturbation is small enough. So the question of assessing the stability properties of a large system gets back to the question of, can you figure out eigenvalues and eigenvectors of a matrix? If you are only able to perform a small number of matrix vector multiplications, and by small number I mean a number much smaller than the total dimension of the system. So let's imagine f u is of a dimension n by 1. So f, of course, is also dimension n by 1, right? Otherwise, you cannot drive a autonomous dynamical system. And this is an n by n matrix. We know that if we make n vectors v, right, that forms an identity matrix, we can just compute dfdu exactly like what we have done. Question is, what if n is a billion? Can we still figure out the properties of the matrix using much, much less than a billion function evaluations? Okay, so the question is, can we compute eigenvalues and eigenvectors with much, much less than n such evaluations? Okay, so today we're going to start with something very simple. That is, we can easily actually compute the maximum eigenvector, maximum eigenvalue and its associated eigenvector using the so-called power iteration. And on Wednesday, we are going to further extend this and figure out if I'm interested in not just the largest eigenvalue and its eigenvector, but also a series of other eigenvalues and eigenvectors, what can I do? All right. And yeah, this is also going to become our first homework assignment. That is, I'm going to give you some example systems, and particularly systems that we can make large or smaller as we want. And I'll ask you to numerically compute the stability properties of these systems. Okay. So the first method is the so-called power iteration. So the power iteration traditionally are used to compute the eigenvalue that has the largest magnitude. And we're going to see we can easily modify it to compute the eigenvalue that is the most positive. So the classical power iteration actually is exactly the way to figure out the most unstable eigenvalue for a map rather than a differential equation. So if you have a matrix A, or let's just say J is equal to dfdu, okay, and you apply J to a vector V, and apply J to the product again, right, and apply to the product again, etc., etc. That can be denoted as J to the power of n times V, where n is the number of such matrix vector multiplications you apply consecutively, right? In reality, of course, this doesn't require you to compute J to the power of n, which requires you to have the matrix J. This just requires you to perform this series of matrix vector multiplications. Each time you are actually just, if you have a nonlinear system, right, you are just applying the system to a slightly perturbed V. So the first application, the direction is V, right? After you compute the output, you then apply J to a perturbation in the new direction, and then you get a new direction, right, and you keep going. And there is a little bit something tricky in here is that after many times iteration, if you actually have a stable or unstable system, the magnitude of the perturbation may become so large or so small that you need to rescale them, right? So the probability of the perturbation being too small. I mean, what's the problem about the perturbation being too small or too large? Anybody can think of like why we want to rescale them so that to prevent them from being too small or too large? Too small would be slow. Yeah. So this. Oh, so here I'm still working on. Yeah, so here we don't have the concept of a time step yet, right? So we are going to look at the differential equation a little bit later to see how this applies to differential equations. But like what did you say about machine precision, right? And the error associated with machine precision is called the round-off error, right? Round-off error is basically when you are working with a perturbation that's so small that it is no longer many orders of magnitude larger than the precision of the floating point, right? You can represent on the computer, and so this is we're going to be talking more about round-off error later, but like one of the interesting thing when we are going to chaotic system, right, is we know that the small error is going to be amplified, right, and it turns out in some cases even round-off error might have huge importance, especially to chaotic systems. But in this case, right, so when the perturbation being too small, the primary motivation to scale them is to avoid having significant round-off errors. Remember when I was perturbing the Lorentz equation, I used the perturbation that's 10 to the minus 8, right? Why 10 to the minus 8 as opposed to 10 to the minus 18? That's because we want to avoid round-off errors. 10 to the minus 18 would really get into the realm that's almost as small as the round-off errors we have in 64-bit double precision numbers. So that wouldn't be a very accurate calculation. On the other hand, how about epsilon that's too big? What if epsilon is, let's say, 0.1? What would be a problem if a perturbation becomes too large? Yes, it may change the behavior because you see, the difference between two evaluations would only approximate the application of the Jacobian when epsilon is very small, right? So if the magnitude of the perturbation is no longer small, the nonlinearity of the system is not going to be negligible anymore. The term that is plus, I mean, here is already divided by epsilon, right? We have a epsilon, we are already divided by epsilon, so there is no longer a square. So this term, is no longer going to be negligible. And this is called not round-off error, but truncation error, right? Because you are truncating the Taylor series. So this is truncation error. As in any numerics, when we are dealing with a nonlinear dynamical system, we have to always be conscious about these two sources of errors. Round-off error on the small side and the truncation error on the large side. We always want to be working kind of in the middle, where neither round-off error nor truncation error is significant. And no matter if j to the power of n makes the magnitude of these larger and larger as n increases, or smaller and smaller as n increases, we are always going to be either going towards round-off error or going towards truncation error. So that's the motivation of actually rescale them, right? Periodically by either dividing by something or multiply something, and then at the end of the calculation compensate it back is usually a good idea. Okay, so this is the basic form of power iteration, and the power iteration gets you what? If you have multiple eigenvalues and eigenvectors. For example, in the 2x2 case, right? So if J, so in the 2x2 case, if J is equal to V times lambda times V inverse, then J to the power of n would be equal to what? Yes, so if you multiply adjacent and multiple J's together, the V inverse at the end is going to cancel with the V in the front of the next J. And only the very first one and the very last one is not going to be cancelled. And in the middle, the lambda is going to be raised to the power of n. Okay, now in the case when you have distinct eigenvalues, right? So for example, in the 2x2 case, if we have two real eigenvalues and they are different, lambda to the power of n would look like a very big number compared to a very small number, right? I mean, the difference between two numbers would amplify exponentially as they are raised to a power of n. So this would be equal to V times lambda 1 to the n, etc. lambda n to the n. Lambda, let's say, well, I think I should not be use n here because I already used the n to denote the dimension of the system. So let's say k over here, and k over here, and here would also be k, and that would be n times V inverse. Now, as long as V does not happen to contain no component in the largest eigenvalue direction, right? So let's say also V is decomposed into V1, etc. to Vn, and my initial V can also be decomposed just like in our previous analysis into a linear combination of all these eigenvector directions. As long as we are not so unlucky that the first component is exactly 0, then the magnitude of Jk times this V, this small v, okay, would be equal to this big capital V, which is the eigenvector matrix, times lambda 1 to the kth power times V1, right? Where V is equal to V1 times let me say just the A1 times V1 plus A2 times V2, etc., where V are the eigenvalue directions, right? The big matrix V is equal to V1, etc., to Vn. Okay, so I'm decomposing this initial perturbation into a summation of different eigenvector directions. Then this is lambda 1 times A1, etc., to lambda n to the kth power times An. The magnitude of this product is going to be dominated by which term? It's going to be dominated by whichever term that has the largest the power of which is growing the fastest, right? So what that means is that if you simply look at the magnitude of Jk times V, it is going to grow like lambda 1 to the kth power, where the lambda 1 is the largest eigenvalue. Okay, so this can be demonstrated by this. So computing the eigenvalue with largest magnitude. So let's actually make another random.rand, this case, let's see, 4x4 matrix. Okay, and we are also going to make a V that's also random.rand length of 4. So let's actually first compute the two eigenvalues. Here, the matrix is still small enough that we can compute these eigenvalues, right? Then let's perform an algorithm. So here is the power iteration. For I, let's say for k in range, let's do 10,000 iterations. Okay, we are going to say v is going to be dot a and v. We are just going to be going this forever. Okay, and we are going to say the magnitudes is equal to, in the beginning, it's just the square root of dot v and v, and every time we do another multiplication, magnitudes would be equal to dot append square root of dot v and v. All right, so then we can look at how the magnitude would increase as a function of time. So what we can do is that at the end, so let's actually semi log y magnitudes and see what this looks like. Okay, so here we can see that the eigenvalues are computed. We get actually two. Oh, okay. So we get two real numbers and a complex a pair. And it does look like this real number has the largest magnitude, right? The complex pair has a magnitude looks like less than 1, and the 1.7 is the one we are really interested in. Here we see a clear slope, right? A clear slope. So what is the so in a semi-log plot, a linear line means what? Exponential growth, right? And well, instead of 10,000 iterations, we can only see about 600 because the number now actually exceeds the range of double precision floating point. But okay, it's almost time to end the lecture. But like we can do a little bit more analysis next lecture to do two things. One is we'll introduce the rescaling, right? Which actually is going to prevent, in this case, from overflow. But in terms of a nonlinear dynamical system, there is going to be nonlinearity way before this is going to happen, right? And if the largest eigenvalue tends to be less than 1 having magnitude, rescaling is going to prevent the roundoff error, right? When we actually get into underflow, right? When the numerical precision is not enough. So, and then we'll also switch to differential equations and apply this algorithm to the Lorentz equation and a larger scale system. I'll see you on Wednesday then.